Good afternoon. Today, the Atom Seminar has the great pleasure to welcome Professor Dirk Gillespie. He currently holds the position of Associate Professor in the Department of Physiology and Biophysics of Rush Medical College. Dirk Gillespie, PhD, is a researcher focusing on the movement of ions, both in biological systems and in non-biological systems. The laboratory of Dirk Gillespie has three main focuses, all studied by modeling and simulations: calcium-induced calcium release, PICR, in cardiac skeletal muscle, calcium movement during heart muscle contraction, and nanofluidics and its applications. His research also includes theory development to improve the modeling of ion correlations. He's the author of more than 70 peer-reviewed research papers. Gillespie is also an editor at European Biophysics Journal and on the editorial board of several other journals, including Channels. In his career, he has mentored 8 undergraduate summer students and 2 postdoctoral fellows and co-supervised 1 graduate student. Welcome, Professor Gillespie. Thank you so much for being here. Please feel free to start your presentation.
Well, thank you all for inviting me. Thank you for Fred and the Adams team. I've been really looking forward to doing this presentation. There. So I'm going to be talking about one of my favorite topics in physics and physical chemistry, which is charge inversion in the electrical double layer. And so even though my interest in ions and electrolytes comes from my work in biophysics, today's talk is going to be all about physics and physical chemistry. And so what I want to talk about in particular are ion correlations and charge inversion. So I will have a brief review of that. And then I want to move into experimental studies along with some theory of those, of some of those experiments where people have studied charge inversion in nanofluidic systems. And in particular, I want to talk about a collaboration that I've been involved with an experimentalist to try to actually exploit and measure charge inversion. And measuring charge inversion has been a sort of a difficult thing in general. And then in the second half, I want to talk about the theory of charge inversion and its origin. So first, I want to talk about just generally about ion correlations that I'm interested in, and I want to consider an electrolyte that is in contact with a smooth hard wall. So in everything that I'm going to be talking about, the ions are modeled in what's called the primitive model. So it's the ions are charged hard spheres and the water is just a background dielectric. So this is the simplest kind of system where you have correlations and effects due to excluded volumes, meaning ions can't occupy the same space, and correlations due to electrostatic interactions, and especially those beyond the electrostatic mean field, which is going to be much of the focus of my talk today. So normally when we think about ion concentration profiles like this, where you have a wall at say x equals 0 that has a negative surface charge. All my surfaces will be negative here in this talk. And then the cation concentration sort of decays monotonically in a Poisson-Boltzmann sort of theory. It would decay monotonically. And then you have your anions here that are depleted. And in this case, we have a jump in the concentration profile because we're looking at the concentrations of the centers of the ions. So when an ion has size, its center can only approach up to its radius, and after that, its concentration is 0. And by the way, I'd like to make sure to say that if you have questions along the way, please feel free to interrupt me. Our seminars, in my university are always full of questions, so I would take no offense at that. So now if you take the same system here and increase the surface charge, if your ions are big, you can get this kind of layering effect where there's a bump in the counter ion concentration, so an increase above bulk for the counter ions, in this case, the cations. And that's because as you increase the surface charge, you get more and more of these hard sphere ions in the first layer. And that makes it difficult to squeeze more ions in there. They just have trouble finding space. And so one of the easiest things to do then is to pack ions in the next layer, which is why you get an increase in concentration here at this sort of radius level and a depletion here in between. And if you take this same system and instead of having monovalent ions like we did here, make multivalent ions, you still get this increase and decay of the cation concentration profile, but you can also get this bump in the anion profile, in the co-ions. And this is what I mean by charge inversion. And so what you wind up having is you have this sort of negative from the surface charge, positive from the cation, negative from this anion bump sort of sandwich that defines charge inversion. And one of the ways I'm in particular going to characterize charge inversion is by the electrostatic potential. And when you have enough of a bump here in the anions, you can actually get a change of sign in the electrostatic potential. So this is the electrostatic potential for this system as a function of distance away from the wall. And that can change sign, and that's what I'm going to be using to characterize whether there is charge inversion or not, because that is a much clearer signal than whether defining that there's a bump here or not. So I'm going to be using classical density functional theory, and I'll give just a very brief overview of it. And this is not quantum mechanical density functional theory of electron orbitals. This is a classical analog for the structure of fluids in inhomogeneous systems. And the idea is that one minimizes the free energy of the system. And there's a theorem that says you can write down the free energy of the system solely in terms of the ion concentration profiles. So you have your densities rho for species I as a function of location X. And there's a theorem that says you can write down the free energy solely in terms of that. And of course, you can break that down into an ideal component, like an ideal gas component, and then an excess component. So the problem is we don't know what these functionals are. We just know that they exist. But if you do know what they are, if you have an approximation of them, then we can minimize that functional with the density profiles and find the density profile at equilibrium, which is solved for by the standard electrochemical equilibrium ansatz, which is that the chemical potential is constant throughout the system. So it's given by the bath. You have an ideal gas component, and then the derivative of the excess it serves like an excess chemical potential. When you have ions that are charged spheres, we break up the excess part into a hard sphere part and an electrostatic part. And there are very good functionals for both of these components. For the hard sphere component, there are a number of very excellent functionals that get the results for hard sphere fluids within a few % of simulations. The electrostatic ones are not as good, but they are quite good. And I'm going to be using this one, which is still, even though later ones have been developed, Still probably the most accurate one out there, although it is more computationally involved, which is why we've been looking at working on other alternative functionals as well. So for the so this is for equilibrium in the cases of nanofluidics where there's also current, ionic current. We're going to be using a local equilibrium assumption and then coupling that with Nernst-Planck or just drift diffusion theory for the ions, and Navier-Stokes for the movement of the fluid. So just to show that DFT is a good description of this kind of model of the primitive model of electrolytes, here's a comparison of the cation profile in the big picture and the anion profile in the small picture as a function of distance from the wall compared to Monte Carlo simulations, which are the dots, and the DFT, which is the solid line in this case. And the dashed line is results from another theory, which isn't relevant for our purposes today. And so, while it's not perfect, the DFT does get all the bumps and wiggles, and this is a particularly difficult case. This is a trivalent cation that is very small, and those tend to be the most difficult cases. So in this case, it's an uncharged hard wall, and then if we put charge on the wall, we also do very well. So we get the decay of the cations, but then we see here that we get the charge inversion that the other theory really doesn't get, and it agrees quite nicely with the Monte Carlo simulations. So that's the DFT I'm going to be using to study the charge inversion. And so now I want to give a brief overview of some work that we've done in nanofluidic devices. And so I want to start with a brief overview. So nanofluidic devices are man-made. They are fabricated in a clean room. And so you start off with a substrate, which is usually something like fused silica. And then using clean room techniques, one etches channels into that fused silica. Those channels are a few microns wide, but in the up and down direction, they are tens of nanometers, and usually the ones that we'll be talking about here are about 100 nanometers. And then you put another piece of fused silica on top, and so you get these covered channels that have a negative surface on the bottom and on the top because silica is naturally negatively charged, and one can also modify those with chemical reactions to change the surface charge. So focusing in on one of these channels, on each end, there's a bath of electrolyte, and so that's why the ions will move through. Then on the bottom and on the top, there's a surface charge, in this case, naturally negative. And then we move ions through here, either by applying a voltage difference or by applying a pressure difference between the two sides. And I'll be showing results from both of those kinds of ion movements. Then in the vertical direction, there are two double layers. So there are on the top and bottom negative charges from the silica, and then two double layers at the top and the bottom. And what makes nanofluidics interesting with new kinds of applications and observed phenomena is that in the vertical direction, it is small enough that the double layers can overlap. And that creates a lot of interesting effects compared to microfluidic devices where this distance is microns and the double layers never overlap. So for this kind of system, ions flow for two reasons. So first is a direct force on the ions, either a concentration gradient, either across the device, or local concentration gradients And then there's also the local electric field that moves ions either locally here or even an applied electric field across the device. And we model those with just a Nernst-Planck equation. And then there's also advected fluid flow. So an electric field acting on a small volume of the fluid itself will move the fluid and therefore the ions that are in there. And also pressure gradients, either an applied pressure gradient or local pressure gradients that are created. And that is all covered in our modeling via the Navier-Stokes equation. So in a nanofluidic device, Kees Dekker's lab at the Technical University in Delft was the first to measure charge inversion. And as I showed you, you have this bump in the anions, sort of in the second layer, which would be sort of around here. And that's what they're going to be exploiting. So in this case, they're using pressure-driven flow. And if the ions in the first layer are considered immobile, then it's the ions in the diffuse layer or the second layer and beyond that make the current. And so if you have in charge inversion, you have a lot of anions there instead of cations, one can change, the idea is to change the current from cation dominated to anion dominated current. And I'll show you some of those results in a bit, but we modeled those with DFT and we wound up not having to have any adjustable parameters because we knew what the ions were and their sizes and their valences. So in these experiments, the charge inversion was created using calcium and a trivalent molecule called cobalt sepulcrate, which is a trivalent cosept that is encaged in a larger spherical molecule, and so which generally goes by the name of cosept. And then we knew everything about the device and the water, and so we could just compute the results that we would get for this kind of system. So this dashed line is the experimental data, the dots here. And so you see that the current, which is on this line, starts off positive and then becomes negative. And what they're changing here is the concentration of calcium. And so it is known that charge inversion becomes more prominent as one increases the concentration of the charge inverting ion. And in the second half of my talk, I'll talk about why that is. And then this is our DFT comparison. And we also get this change of sign of the cation dominated to anion dominated. When the charge inverting cation is cosept, they do the same experiment, just changing the concentration of cosept, that in this case is the dots, and our DFT again is the solid line. And we also get certainly qualitatively what the experiment finds, a change of sign, and this kind of minimum. And we also are able to reproduce with the modeling a competition between ions. So here, the concentration of cosept is fixed at 1 millimolar, for example, for the red curve, which would be about here. And then there's more and more potassium added to the system. And what happens is that then the current becomes cation dominated again, but there's also a maximum in, which is also something that the DFT results get. So the DFT here is certainly qualitatively correct. And that, I think, from a physics point of view, is the most important part. It is not quantitatively correct. We miss the onset of the change of sign of the current by an order of magnitude. But I think given that we're using this incredibly simple model of the electrolyte as just charged hard spheres, this is pretty good. And if we want to understand the physics, I think we show that the DFT contains all the relevant physics. And so that was my first sort of foray into studying nanofluidic systems and charge inversion experiments. And over the last few years, I've been collaborating with Professor Samita Penatur at the University of California in Santa Barbara. And charge inversion is one of those things that we both have an interest in. And we have two projects that I want to briefly go over. And the first one is where we created a stable front between two electrolytes using charge inversion. And the application of this is to concentrate ions at that interface. So say, for example, you have a very low concentration of some sort of analyte that you're interested in, and it is easier to study that if you can pre-concentrate it. And the idea is that one can pre-concentrate the ions at this interface. So that will be the application of it. So the system that we're using is this kind of nanofluidic channel that is connected to two wells. And in this case, the driving force is an electrical potential difference. And what we get here is, so this is a top-down view of the channel. So this white line is the channel. That would be like going this way between the two baths. So in one bath, we have magnesium, which is down here, and that is the non-charge inverting ion. And in the other bath, and that's up here in this picture, we have something called rubipi, which is a ruthenium that is encaged as well, similar to the COSEP. And that is going to be our charge inverting ion. And one of the nice reasons to use rubipi is that it is naturally fluorescent. So this is actually just a light microscope picture of the fluorescing rubipi without an electrostatic potential applied across the system. So it's just diffusing down in here, so you can sort of see it taper out. And when we apply an electrostatic potential, we get a very sharp junction between the magnesium-filled electrolyte system, which is in the lower half, and in the upper half, the rubipi side, the rubipi containing solution. And the reason that we get a stable front here is because of the charge inversion. The charge inversion makes the fluid flow in each of these different compartments go in opposite directions. So here the fluid in the charge inverting side, it goes this way, and in the magnesium filled side, it is going this way. And when they meet, they one is not driving the other one in either direction, and they just meet at a stable front that doesn't move very much at all. And so if there was no charge inversion here, we would get something like an isotachophoresis system where you get a front between them, but that front will move. And in this case, this front is stationary. And so we could, in principle, pre-concentrate analytes here for a very long time. So that is the first project. And it's just sort of a brief overview. I want to talk about the theory of charge inversion more, which is why I'm sort of going through this a little bit faster. The second project is looking at the dynamical onset of charge inversion in experimental systems. So here we are using the same system, except that this time we're using lanthanum instead of rubipi as the charge inverting ion. And lanthanum is different in that it adsorbs to the charged walls much more slowly than the rubipi. Once we turn on the voltage for the rubipi, that stable front formed within a second. Here, the timescales are much different. So we start off, and so we look at the current as a function of time for this kind of system. So we start off with a system that has only tris, which is not charge inverting, and then we change the composition of the well of this bath over here with lanthanum, which is charge inverting, apply the potential, so that's here, and we get a positive current because now cations, the lanthanum is moving into here, and then as it slowly adsorbs to the surface, it starts to cause charge inversion, and then the net velocity of the fluid moves backwards, and so you get this kind of reversal, and it keeps going because places that had been charge inverted now slowly desorb the lanthanum, and so it is not, so it keeps going down because these areas keep changing. And so this is a new way of looking at and being able to actually measure some aspects of charge inversion. And part of what has hindered the study of charge inversion, I think, is that there are very few experimental systems where that can be done. And so we want to exploit this some more. And this is a very easy technique that is commonly used called current monitoring. It just hasn't been applied to this kind of system. So that's the kind of work that we've been doing on the experimental side. So now I want to finish up in the last while and talk about the theory of why charge inversion happens. And this is what is closest to my heart, is the physics and understanding the physics of the charge inversion. So we start again with the minimization of the functional to get to the equilibrium equation that the electrochemical potential is constant everywhere. And for the charged hard sphere system, we're going to break this term, the excess term, down into 3 parts. So the first is just the mean field electrostatic potential from the Poisson equation. And if we only had these terms up to here and forget about these, then we just have a Poisson-Boltzmann system. And then we also have a hard sphere part. So the part that says that 2 ions can't overlap. And then we also have this screening component, which is going to wind up being the most important for charge inversion. And so what this does, it describes electrostatic correlations beyond the mean field. So it's the ability of an ion to screen other ions within roughly a Debye length. So the way I like to think about it is that if you just have a homogeneous system, so just a glass of salt water, the energy that it takes to insert a particle, which is the electrochemical potential, is different if you have sodium chloride dissolved in water or whether you have a calcium chloride dissolved in water. For that kind of system, if the concentrations are the same, the ideal gas part is the same, the mean field is 0 because you're in a bulk system, the hard sphere is the same, the ions have the same size, and so the energy that it takes to insert another ion is very different in these 2 systems because of this term. And that's because the ions rearrange around each other very differently if there is a divalent cation versus, like in calcium, versus a monovalent cation. And in something like a Debye-Huckel theory, that is the kind of term that is being described by Debye-Huckel, which is the energy of the ion interacting with its screening cloud. So this is going to be a major focus of this work. And so we're going to rearrange this and look at the density profile as a function of these different components. And we're going to look at all these components all the time. And the delta means relative to bulk. So you have the bulk components subtracted off. And then we're going to look at all of those different components just for the cation, because those are the ones where that are in the double layer mostly for our negatively charged surfaces. And we're going to look at them only at contact, so only at the x equals the radius of the cation, because that is the closest that they get. That's where the action is. And I want to look at all these things as a function of surface charge. And so I only want to plot one thing. And so the one location to do that is at contact. So that would be right here in these kinds of density profiles. We're looking at all those three different components just here. And we're going to take this and rearrange that so that at contact, so this is always at contact. What we're interested in is the electrostatic potential at contact. So this is not the surface potential, but rather the one at contact. And we want to look at this in terms of these other components, the screening component, the hard sphere component, and what I call the adsorption energy. So that's just the log of the ratio at contact, of the concentration at contact with the bulk concentration. So we're going to look at this in terms of all of these three components as surface charge increases. And the question that we have for charge inversion is this potential here positive? So here as the sign changes from negative to positive, if there's a positive thing, we're going to say that that's charge inversion. So if this is positive at this one location, we know that there's charge inversion. If it's negative, we don't know, because maybe contact is here and we're looking at something that's still negative and the positive part is away from there. But if it is positive, we know that we have charge inversion. And then we're going to look at how that happens because of each of these components. So we know that the adsorption energy is going to be negative. This minus E term is going to be negative because the concentration at contact is always going to be above bulk. And so the negative of that is negative. The hard sphere one is also going to be negative because this is with respect to bulk. So it is easier to, it is more difficult to insert a particle into this dense area of ions than it is into the bulk. And so when you take the negative of that, this term is also negative. So if there's charge inversion, that means it can only come from the screening term. And that term is also, we know that this term is also going to be positive because the screening component becomes more negative. It tends to be a negative thing, and it becomes more negative the higher the concentrations. So at these high concentrations here, this will be more negative than here. And then when you take the negative sign of that difference, you get a positive term. And so we already see that the screening component is the one that is going to make the charge inversion happen. And so we're going to look at this a little bit closer. So here we have that same equation, and we're going to look at all of these different components as we increase the surface charge. And I'm going to take you through all these four panels so you don't have to try to figure out what's going on right now. So in each of these panels, the black line is the electrostatic potential at contact, and the green line is the E term. So it is positive. And then I've also included as the dash green line, the minus E term, so that it's for reasons that will become clear in a minute. I want to include the minus E term explicitly. The delta mu HS, not the minus, just the delta mu HS is in blue, and we see that it's positive when we do have it. And then the screening term is in red, and we also see that when it occurs, it is negative. So let's take a look at this first system. So here we're plotting each of these as we're increasing the surface charge, and the surface charge is negative, but we want to see it increasing, so we plot it this way as the absolute value. So here we have a monovalent system with the anions. The anions are always going to be a -1 anion. of this size of 0.3 nanometers. And in this case, we're also going to have the cation be the same size. So this is at very low concentration, so 10 micromolar. So this is a system where we don't have really any contribution from these terms. So it's more like a Poisson-Boltzmann system. And we see that the black curve, the electrostatic potential, which we want to see whether it becomes positive at some point for charge inversion. So in this case, it just stays negative and it follows the minus E curve, the dashed green line. So this is just very much like a classical sort of Poisson-Boltzmann result. Then we take the same system and we just increase the size of the cation. So everything else remains the same. So in this case, the hard sphere component is very significant because the ions are quite large. And what happens is, as we increase the surface charge, is at the beginning, the black line still follows the dashed green line. So this, the hard sphere term is not contributing a lot. So we're in this classical Poisson-Boltzmann regime. But once the hard sphere term starts kicking in, it makes the electrostatic potential much more negative than the classical case. And so what is happening here physically is that the double layer is becoming very crowded and it's difficult to find space. So this term is positive. It takes a lot of energy to insert a particle into such a dense space. But in order to have charge neutrality in the system must draw in more and more ions as the surface charge increases. So that requires a more negative and a more negative potential. And so if the hard sphere term is dominating, you wind up getting a potential that is more negative than the classical case. So now let's take a look at this third case where we're going to be focusing on the screening term. So here we're going to have a small ion again. You don't have a lot of hard sphere contributions, but we're going to be increasing the size of the concentration of the ions. And so in this particular case, there's a small contribution from the screening component. And so here we see again at the beginning, we get a classical sort of Poisson-Boltzmann result. And then as the negative screening term starts to contribute, what happens is that the electrostatic potential becomes less negative than it would be in the classical case. And if we amplify this screening component by having a multivalent ion, then we see that that classical regime is very limited and the screening component becomes negative and has a very large negative contribution, and it is initially making the potential less negative compared to the Poisson-Boltzmann, but eventually is the one that drives it positive. So why does making it divalent have such a big effect? That is because the screening component, which is now quite big, the screening component is roughly proportional to z squared, so to the valence squared. So this one is going to be 4 times essentially this one. And that is why, one of the reasons, that is why multivalent ions have much more charge inversion than monovalent ions. So I want to look at one last thing, which is why the charge inversion becomes more prominent as we increase the concentration. So if you remember in the Decker experiments, they increase the concentration of both calcium, which would be something like this monovalent, this divalent, and the cobalt sepulchrate, which would be this trivalent, and they found more and more charge inversion. So why is that? So here again, we have these components as a function of the surface charge, but this time at different bulk concentrations. So what we see is that at low concentrations, you get this classical result where the potential follows the adsorption energy. But what you see is that this adsorption energy changes a lot as you change the bulk concentration. On the other hand, the screening component, the red line, doesn't change much at all. It changes some, but it doesn't change nearly as much as the adsorption energy does. And so why is that? The adsorption energy changes a lot because you're directly dividing by this bulk concentration. And the contact concentration is going to be relatively unchanged. It doesn't really care about what's happening in the bulk. If you have a large surface charge, this is going to be relatively constant. And we can talk about more about that in the question and answers if you want. But essentially, you're dividing a constant by this changing number. And so that is what is driving this big change in the adsorption energy. And so what you see is the sign of the electrostatic potential changes, in this case, when these two lines cross. And so you have these big changes in the green dash curve. And so that crossing point moves over very quickly. So where it's not even crossing here is now maybe starting to cross here, and then you get it here, and then it moves over to here. And it is this kind of energy balance that is causing the charge inversion to increase as you increase the surface charge, where your screening component really doesn't care about the bulk concentration, but the adsorption energy changes quite a bit. So I want to summarize in the last couple of minutes what we found in this paper, that there are basically three regimes that happen in the double layer as you're increasing surface charge. So for this, I want to not only talk about the screening component, but I want to talk about the excess component as a total, as the hard sphere plus the screening component. So here we have those same kinds of plots, this time for a divalent and a trivalent at low concentration. And I want to go through quickly these stages of the double layer as we increase surface charge. So at low surface charge, you just have the classical Poisson-Boltzmann case where the excess component isn't contributing a lot. And in the second case, you're getting an electrostatic potential that is less negative than the classical case. So the black line is above the green dash line. And that's because the excess term is negative, and it is negative because the screening term is dominating over the hard sphere term. This term is always negative, this term is always positive. So this term is negative, and so that makes putting ions in easier. You don't need as much electrostatic potential as you would if that term didn't exist, which would be the classical case. So then the final case is when you get really large surface charge. That is when the excess potential starts becoming positive. So the excess chemical potential becomes positive because now the hard sphere term is dominating. You get so many ions into that first layer that it is so dense that it is really hard to fit in ions. And so this term, the excess becomes positive, but to have charge neutrality, you need to drag in more and more ions. And so that makes the electrostatic potential, that forces it to become more and more negative, and more negative than in the classical case, to counteract that large positive potential. So that is what I wanted to talk about. Again, thank you very much for inviting me. I want to thank my collaborators, my longtime collaborator, Deja Boda, who did the Monte Carlo simulations that I showed you at the beginning. A very talented undergraduate student that I had a couple of years ago who did all the work on this last theory of the 3 stages of the electrical double layer, and my wonderful experimental collaborator at UC Santa Barbara, Sumita Penatur, who did all the experiments on the charge inversion that I showed you. So thank you very much. This is what I wanted to talk about. Let me see if I can.
Thank you so much, Professor Gillespie. We are now open to questions. If you want to ask one, you can feel free to raise your hand using one of these Zoom tools. You can also ask questions by writing on the chat. And our YouTube viewers can also ask questions by writing on the YouTube chat. So who wants to be the first?
Yeah, hi, I have a question. So,
You can go ahead.
yeah, so I'm a PhD student in Berkeley and I also work on charge inversion, but we use a different approach. So my only question is that have you also tried this method for?
Sorry, can you open your camera, please?
Okay.
Can
Yeah, hi.
nice, thank you.
Yeah, sorry about that. So yeah, so my only question is that have you tried to model like charge attraction also? Because the physics is same, right?
Right, I have not actually looked at like charge attraction. My focus has been sort of on the double layer itself, and moving into like 2 double layers is something that that I want to do in the future. But no, I haven't actually specifically looked at that case. I've been focusing on the 1 double layer because I've been wanting to understand the physics of what's going on in that one particular case.
Okay, and one more small thing. So have you seen a, what should I say, a re-entrant type of behavior where you go from, when you first see inversion, then you again see re-inversion. Basically, you go back from negative to positive at very high concentration. So that is also something people have seen in simulation.
So let's see, I just want to make sure I get the question correct. What is the parameter that is being varied? Like when you say change?
Change the bulk concentration of the divalent or trivalent ion. So as you increase, you see inversion. So do you go back from inversion to normal case again?
Yes, the charge inversion will go away with different things. Yes, you can get that. Certainly as you're increasing the surface charge, because of that, increasing the concentration. I think I haven't looked at it to that high a concentration. Probably, I'm guessing that this is going to be more difficult to see in the primitive model because in the primitive model, your ions are essentially a gas. And so if changing the bulk isn't going to change things a great deal, I think. Let's see, that's probably the best answer to my question, to your question that I have, unless you want to rephrase it.
So my understanding is that at very high concentrations in the bulk, the correlation strength is very high in the bulk. So ions don't have a need to come to the surface.
Yes, so if you have like, for example, in the primitive model, if you have very large ions at high concentration, yeah, you start to get things, you get at a large adsorption already, a large concentration already. Yes, definitely we see that. And so that is, that is not something I guess I've studied a whole lot. We've gone up to like 1 molar, but not fantastically more. One of the reasons is that, let's see, I'm trying to think of some of the work that I've done with Sumita that about this kind of thing. So yes, it goes away, but I don't remember the where we had large ions, but I don't remember the exact reason. I don't think I studied it, but there that has to do with the pressure that you're getting in the bulk, and that is pushing ions basically into the wall. And so in the something I didn't discuss was that in the primitive model, you have this contact density theorem that's an exact relationship between the densities at contact and the pressure in the bath and the surface charge. And I'm generally looking at regimes where the pressure is not important. And so I've been focusing more on those kinds of areas. Once you do increase that pressure with very large ions at high concentration, yes, that starts to have an impact there, but I haven't studied that in detail.
Okay, thanks for the answer.
Georgian Lounge wants to ask a question. Could you open
I
your
do.
mic?
I do.
Yeah, I have it in.
We have a question on the chat first,
Yeah,
Professor Fred.
I have it in front of me, I can read it. So my first question is, for highly polarizable ions, that do not behave like charged spheres, what is the most commonly used electrostatic potentials in DFT? Like, how do you do, I think the question is, how do you do DFT for highly polarized ions? And I don't think we have a good answer for that. I don't know of one for polarizable ions. It has been difficult enough coming up with functionals for fixed charge ions, and polarizability, even just not having polarizable ions, but having like a polarizable wall, that is also still a really open question. And I published something on that, and I think it's actually completely wrong. And so I think we need to go back to the drawing board on anything that involves polarizability in DFT. The second question is, in the equation of the chemical potential in the bath, how does the conductivity of the ions, lambda, in the studied system, how can that be estimated? Such a parameter depends on several experimental conditions. Yes, so the chemical potential is an equilibrium property, so it doesn't really contain conductivity in and of itself. So in equilibrium, especially, which is where I've been focusing, the conductivity doesn't come into it at all, because the chemical potential depends only on like the particles themselves, not on how they move. In the other studies that we did with current, the conductivity comes in by giving ions a diffusion coefficient, and that in the Nernst-Planck equation, and that is about it. That's how we do it for that system. For systems where, for example, for this system where we had the stable front, we did a theory of where the stable front comes from, and that did involve conductivity, but that's a more sort of basic, sort of more macro scale argument for pressure and mass balancing, very akin to isotachophoresis kind of modeling. And there we just use the straight conductivity, and usually we use directly measured ones for exotic ions like group IPI. That's probably as best as I can answer those questions, unless I misinterpreted them.
Okay.
I have a question.
You can go ahead now, Professor Fred.
I like the small device, nano device, and I wonder, I want to understand better your approach. First, what do you think that the rule for 3D DFT can help to describe this? because as I don't know if I understood correctly, but I think you use 1D DFT.
We did use 1D DFT. I think there is definitely some aspects for like a 2D DFT for this kind of system, absolutely. So what we did basically was just model the, model this cross section of the double layer with a 1D DFT. And because we had equal concentration in both baths, we didn't need more. So we didn't have a concentration gradient. We could do the applied pressure or the applied potential just as a linear drop across the system. So that's how we could get away with doing 1D DFT. There are definitely things that are open for doing 2D DFT, for including the up here and the across the system. For entrance effects, that is definitely an area that can use work for this kind of system. And for having these kinds of sharp interfaces, or interfaces where you have two different ions moving in two different directions, that you definitely gonna need a 2D DFT to do that. And like, for example, like for a system like this, we didn't actually do DFT on this system. We did simpler kind of modeling for the, figure out where this front is, and to model sort of this kind of effect in terms of adsorption. But because for 1D DFT, you can get away with it if you don't have concentration gradients. But if you have concentration gradients, especially like two different kinds of ions in each bath, you're definitely going to need something in the axial direction versus, and then also in the transverse direction.
Okay, thank you. For the first device, you use Navier-Stokes equation together with DFT.
Yeah.
What the size that we can still believe in Navier-Stokes equation? That's more philosophical question, but I'm sorry for that. But I'm curious about what you.
So certainly, we have not seen any breakdown of like it not working. You know, that's probably the best answer I can give you. I don't do a whole lot of fluid mechanics, and so this group has been using this kind of modeling with Navier-Stokes, and everybody else in the system has as well. So that's why I used it. It's an easy coupling if you have no concentration gradients. But so far there really hasn't, it's always worked. So I think we keep using it. The one question, once you get into this kind of area, is where's the slip plane? Where do you put the boundary condition? That becomes first order important for these kinds of systems, because now you can't sort of ignore this first layer, and the Navier-Stokes becomes important. You get reversal of fluid flow. I know you're around here somewhere. Oh yeah. So when you have a change of potential, the fluid flow reverses because you have this change of potential, because you have the fluid being driven by the sort of electrostatic potential, but it matters where you put the boundary condition. If the boundary condition is negative, like down here, then your fluid will drive mostly in the direction that you normally have. If your boundary condition is here in the positive, then the fluid will move in the opposite direction. And so we placed that boundary condition sort of at the diameter of the first one, but this is very ad hoc theory. It's just sort of because it worked. And so that is an area of the Navier-Stokes that is definitely going to need attention, And if that is where the Navier-Stokes is starting to break down, because those sorts of seemingly small changes have big effects on the final current.
Yeah. Thank you. As you treat real ions, and you have no exactly primitive model in this small device, what do you think is the rule for the water, explicit water, or even more important, the interaction between ion and the interface in this so small device? You know, I mean,
right.
maybe the small force that you are neglected in this small device maybe plays a very important role. I don't know.
Yes.
What your opinion?
So certainly in this direction, you're going to get a lot of oscillations in the ion profiles just because water is there. That's pretty well known. So yes, we are ignoring that. So so how can we get away with something like that? And this is actually something that I've been working on with my friend Deja. And one of the things he's particularly interested in is exactly this kind of question. How can one get a device function from a really simple model? You know, even like Poisson-Boltzmann, in some of these cases, you do pretty well. How can such a simple model give you a good answer for predicting device current? And the answer in a series of papers that he's responsible for, he's done, it's all his work, is essentially that what matters is less the local interactions and the local structure, but if you get the to get the device physics, you have to get the device physics generally correct. So that means converting an input voltage into a current. And that does require a profile across here, but that profile doesn't have to be perfect with some effective parameters like an effective diffusion coefficient. If you use a diffusion coefficient from one case to set the scale of the current, then you can use that same diffusion coefficient and get the general device physics correct because your physics from here to here is dominated by certain things that happen inside on this kind of centimeter scale, and the local nano scale is less important. It is more important that you get the phenomena like charge inversion that you need to have, rather than the exact details of all the layering and stuff. And he has a number of papers in cylindrical nanotubes or nano systems where he drives current and with molecular dynamics and this kind of primitive model, and the primitive model gets the device characteristics certainly qualitatively correct, and with an effective diffusion coefficient that is essentially picked once to set the scale of the current, it gets the current quantitatively pretty correct as well. And so it's a matter of the question that you're asking about device physics versus the exact local structure. If you're interested in the exact local structure, no, this is not a good model. If you're interested in device physics, which molecular dynamics can't do, then there's actually another aspect to it that where you can get that correct, the inputs outputs of the device correct.
Thank you.
Okay, do we have another question? Well, I think it's time to wrap it up then.
Great. Thank you again so much. This has been a lot of fun. And like I was telling Fred before the meeting, I have already talked to my department about doing something like this so that we can get people from all over the world to talk to us.
It's an honor to have you here with us, Professor. Thank you so much for your presentation. And now we are headed to the final announcements.